In the last segment, we talked about Gibbs free energy and the fact that for the most part, we're going to look at enthalpy as the driver of Gibbs free energy. And that the heat of the system is the negative of the heat of the surroundings. And when you look at the units cancel to give you a heat unit, such as joule or kilojoule or calories or kilocalorie. Now what we'd like to do is look at reaction rates, equilibrium, and kinetics. So your generic reaction like this means that in order for A to B to form C and D, they have to come together. Okay, so the A's over here, the B's over here, they have to come together. And in coming together, it takes energy to do that. So all reactions will have a general activation energy of which you have to put energy into it to get it to go forward. The transition state is what we call an activated complex, and your products are over here. So your reactants on the diagram are right here. Your products on the diagram are right here. The activation energy is here, and the activated complex is on the top of the graph. Page 5. If I have a generic reaction, A plus B goes to C plus D, I can write a graph. I'm going to call this the reaction coordinate. And my energy is over here, and I can use whatever unit I want. Let's say kilojoules per mole. 0, 20, 40, 60, 80, 100, 120. Okay, so let's say our reactants start at 40 and our activated complex goes all the way up to 120 and our products come all the way down here to 20. Okay? Now let's put a catalyst in there. The catalyst will work by lowering the activation energy, and let's say for kicks and giggles it's going to lower it to 80 on our graph. Okay, so what is the energy of the reactants? Well, the reactants are right here, so that's 40 kilojoules per mole. Okay, what is the energy of the products? 20 kilojoules per mole. What is the activation energy of the forward reaction? Well, I'm starting at 40 and I'm ending at 120. So it's 120 minus 40, or 80 kilojoules per mole. If I put the catalyst in, now I don't have to climb to 120, I only climb to 80. So 80 minus 40 is 40 kilojoules per mole. Now notice that these are all positive. These are all requiring energy. Okay? Now what is the enthalpy of reaction? Well, I start at 40 and I end at 20. So my enthalpy of reaction is right there. Okay? So I end at 20, I begin at 40. So just like your stocks or your checking account, when you start with $20 and you take out $40, you have a minus 20 kilojoules per mole. And because that is minus, that is exothermic. Okay? So what this is saying is that this reaction is generally favorable, and with a catalyst, the reaction will just go faster. Okay? Now we're going to contrast that now with a reaction. Okay, so reaction coordinate. Our energy, let's call it kcals per mole now. 0, 50, 100, 150, 200, 250, 300. Okay, so let's start this one at 50 go up to 300, and let's land at 200. Okay? Let's put the catalyst in, and let's say the catalyst now peaks at 250. Okay? What is the energy of reactants? Well, that's 50 kcals per mole. We see it right there. What is the energy of the products? Well, that's right here. 200 kcals per mole. What is the activation energy of the forward reaction? Well, I start at 50, I land at 300, so 300 minus 50 is positive 250 kcals per mole. If I put a catalyst, I don't have to go to 300, I only have to go to 250, but I still have to put 250 minus 50, or 200 kcals per mole into it to get it started. Enthalpy of reaction starts at 50, ends at 200. Enthalpy is right here. And this is a positive 150 kcals per mole. I start at 50 and I land at 200. Okay, so 200 minus 50 is 150 kcals per mole. Okay, so this is endothermic. The point being is, even with a catalyst, this reaction is not going to be particularly favorable going forward. Not favorable, even with a catalyst. Okay? All right, on the next page, what we want to do is we want to have something that's reversible. Okay? So we'll make another graph. This is going to be our reaction coordinate. This is going to be our energy, and how about we call it kcals per gram. 0, 50, 100, 150, 200, 250, 300, 350. Okay, 50, 100, 200, 250, okay. So let's say on this one that I start at 200, I go to 350, and I land at 50 over here, and I put my catalyst in, my catalyst goes to 250, and there's my graph, okay? So the energy of reactants is going to be 200, okay? And so for the sake of moving along, I'm just going to leave the units out. They're kcals per gram. Enthalpy of the products are right here, and that's 50. Activation energy starts at 200, goes to 350. So that's going to be positive 150. Okay, when I put the catalyst in, it lowers it to 250. So now I'm putting in 200. I start at 200, I go to 250, so the activation energy of the catalyzed forward reaction is plus 50. Okay, so now I want to go backwards. I'm going to start at 50, and I'm going to end at 200. So the enthalpy of reverse is positive 150. Okay, plus 150 kcals per gram. So in the reverse reaction, it's a positive, and this is endothermic. Okay? So the question is, which direction is probably favored? The forward, which gives us a negative enthalpy, or the reverse, which gives us a positive enthalpy? Well, it's probably going to be the forward. And we're going to take another look as we move along about other indicators about whether the forward or reverse reaction is favored. We tend to think of our symbol there as being equal, but that's not the case. Okay? Now, in general, endothermic reactions tend to be non-spontaneous as written. In general, exothermic reactions tend to be spontaneous as written. And Gibbs free energy, while it's a combination of enthalpy and entropy, unless we put heat into it, the driver of Gibbs free energy, for the most part, is going to be enthalpy. So negative delta H will tend to give us a negative delta G. So we're going to simplify our lives and look at enthalpy as the driver. Okay, now how can we get this to go forward? Well, again, we talked about the temperature. We also have the structure itself. We have the shape and the orientation. That's particularly useful when we get to enzymes. Concentration or molarity. Physical state. Is there a lot of surface area in a gas, for example, or a liquid, for example, or a small amount of surface area, for example, in a solid? And then, of course, the catalyst. And we've already seen that the catalyst will lower the activation energy, but even with a catalyst, sometimes, like for example, when this one goes backwards, even with a catalyst, it's not enough to overcome. Now the question is, what happens if the reactions still aren't favorable as written and we still want them to go forward? In the next segment, we will look at how we can achieve that.